Hello everyone, welcome to my channel Chemical Engineering Zone. In this lecture we will discuss about humidification operations. So this is chapter number 19 in the book of Unit Operation for Chemical Engineering, 7th edition. Unit Operation for Chemical Engineering, 7th edition, and this is chapter number 19. So humidification operation. So the humidification operation are very important in the chemical industries. These humidification operation are also used in the humidity charts, to make humidity charts. In the cooling tower we can also use this humidification phenomena. So first of all we should know about the humidity. So the first topic in the humidification operation is humidity. So humidity is nothing but it is the mass of the vapor. It is the mass of vapor divided by mass of vapor free gas. So or it can be mass of the vapor divided by mass of carrier gas. So this is the humidity, definition of humidity. So it is the mass of vapor which are carried by vapor free gas. So mass of vapor divided by mass of the vapor free gas, and humidity is denoted by this symbol. You should know this is the symbol for humidity. Now there are various systems. These vapor can be the vapor of water. These vapor can be vapor of water like H2O in the vapor phase. These can be the vapor of benzene. These can be the vapor of hexane, or some other organic compound. And the carrier gas can be air. It can be some other carrier gas. It can be propane, it can be butane, or it can be some other gas. It can be other carrier gas. For example, we are considering a air water system. So suppose we have air water system. This is water. This is the water, and the air is flowing across the water. So this is the air. This is the hot air. The water is our component A. When the hot air is passing through the water, the cooled water, this is the water, liquid water. In the hot air passing through the liquid water, the air will give some of its heat to the liquid water. The molecule of the liquid water will become heated up. After heating, the liquid molecule will convert it into the vapor phase, and the water vapor will form on the surface of the liquid water. So when the air molecule give its heat to this liquid water, the water molecule will become heated, and after becoming heating, the liquid water molecule will the temperature of the liquid water molecule will increase. As the temperature of the liquid water molecule increase, the liquid water molecule will convert it into the vapor phase, and the water vapor will form on the surface of the liquid water. So now remember that this gas is not, that this air will not dissolve in this liquid water. We assume that the gas will not dissolve in this liquid water, so it will just give its heat, and the water vapor will form. Now this is the air molecule. Suppose the air molecule are like this molecule. So when these air molecule give its heat to a liquid water, water vapor will be formed, and a mixture of water vapor and the carrier gas will form on the surface of the liquid water. So this carrier gas will carry the water vapor with itself and across in this direction. So the carrier gas will carry the water vapor with itself in this direction. So what is humidity? Now it is the mass of water vapor, the mass of this water vapor, these are water vapor. So the mass of these water vapor, which are carried away by the mass of carrier gas, So the mass of water vapor carried by mass of carrier gas is called humidity, or the mass of water vapor which are present in the mass of carrier gas, which can be air or benzene or some other gas. The mass of carrier gas is called humidity. So this is the humidity. Now the water vapor is our component A, and suppose the air is component B. The air molecule is component B. So this is component B molecule. This is component B. Air is component B, and the water vapor is component A. So the mass of component A, or the mass of water vapor, mean the mass of component A to the mass of component B is called the humidity. Now we can also, now the humidity, now we are assuming that this water vapor and the air molecule will obey the ideal gas law. So we will apply the ideal gas law to the water vapor and to the air, or to the carrier gas. So we know that PV is equal to nRT according to the ideal gas law. For component A, partial pressure of the component A, or the partial pressure of water vapor into volume of water vapor into the mole of water vapor into RT. These two are constant, universal gas constant and the isothermal condition. Similarly, for component B, P is equal to mole of component B into the RT. Now we know that mole is nothing but mass of component A, mass of water vapor, divided by molar mass of component A. Mass of mole of component B is equal to mass of component B divided by molecular weight of component B. So the molecular weight of A of the water is 18 gram per mole. We also know that from periodic table. And the molecular weight of air is 28.98 or 29 gram per mole. So we can put this equation, suppose equation number 1, and this is equation number 2, and this is equation number 3. So put equation 1 and 2 in equation number 3, we will get the definition of humidity, which is mass of, so we can further simplify this equation 1 and equation number 2. For example, phi A into V is equal to mass of component A, molar mass of component A into RT. So from this, similarly for component B, phi B into V is equal to mb into RT. So rearrange, we will get Ma, and rearrange this equation, we will get m mass of component B. So after rearranging, we will get the definition of humidity, which is the phi A into V, molecular weight of component A, divided by RT, and divided by molecular mass of component B, which is equal to phi B into V, molecular weight of component B, into the RT. This cancel with this, this cancel with this, because volume occupied by component A is equal to volume occupied by component B. You can also say that the two gases are occupying the same volume, the same mixture, so you can also, so we can this volume occupied by water vapor is equal to volume occupied by the air molecule. So we are assuming that VA is equal to VB, and the R and T are the constant. So the humidity will be equal to partial pressure of component A and molecular weight of component A, and partial pressure of component B into molecular weight of component B. So this was component A, water vapor, and this was the carrier gas molecule. So the partial pressure of water vapor is denoted by phi A, and this was on the surface of water. So the partial pressure of water vapor is denoted by phi A, and the partial pressure of carrier gas is denoted by phi B. So, and the total pressure according to the Dalton law, that the sum of partial pressure is equal to the total pressure. So PA plus PB will be equal to total pressure. And total pressure usually the total pressure is 1 atm in most cases. So from this we can also write that PA, molecular weight of component A, and in place of phi B we can write that PA plus PB is equal to phi. So P minus phi A is equal to phi B. So P minus PA is equal to phi B, and to the molecular weight of component B. Molecular weight of component A is, this is the water vapor, and molecular weight is 18 gram per mole, and this is the partial pressure of component A, and the molecular weight of the air is 29, suppose, gram per mole, and 29 gram per mole, and this is the P minus P A, and this P is in most cases 1 atm. So from this we can get the humidity of water vapor in the carrier gas. Thank you very much for your attention. In the coming lecture we will discuss about the wet bulb temperature and the dry bulb temperature. We will also discuss the humidity chart and the psychometric chart. We will also discuss about the cooling tower in this chapter. Thank you very much for your attention. If you are new to the channel, please like and subscribe. Thank you very much.